Hello and welcome to Galactic Developments. Galactic Developments is a history of the future told in many events on a common timeline. Year 3308. Supernova. A supernova occurs only once every 100 years in the Milky Way galaxy. And a supernova within our reach is even more unusual. Since humanity can only visit a small fraction of the galaxy, there is only a 1 in 100 chance that a supernova event is so close that we can fly there. So, it is quite a coincidence that a supernova occurs just 5,000 light-years from the Earth, in the Orion Arm. That is only a year's flight time. Not close, but feasible. For a long time, this supernova candidate has been under scientific observation by many species. The star cannot be seen from the Earth because it is hidden behind an interstellar dust cloud. However, it illuminates the cloud and the entire formation is well visible from the Earth. Even before the age of spaceflight, it was long suspected that the dust cloud might hide a very bright star. The star was actually discovered by the GAPAX mission, which was able to see the remote side of the interstellar cloud. GAPAX stands for Galactic Parallaxes, an expedition that started in 2702 to travel from the Earth to the edge of the Milky Way. The star is a so-called red variable hypergiant. Its changes in luminosity had long been observed as brightness variations of the dust cloud. Many research organizations have installed their instruments around the red hypergiant. Radiation detectors measure the star across all electromagnetic frequencies. Particle detectors measure the flux of known and hypothetical particles, from neutrinos to gravitons, from relatively slow mass ejections to ultra-fast cosmic rays. Neutrinos, escaping unhindered from the interior of the star, provide a live view into the stellar core. Gravitational waves also show the deformation of space in real time. All those sensors feed huge amounts of data into computer models and simulations. A few years before the explosion, the models start moving. The computed probability of a supernova event increases strongly. It grows from the normal background probability of 1 in a million per year, to 1% in 3250, and then to 10% per year in 3300. Thus the supernova explosion does not come as a surprise. Many astrophysical organizations of the human sphere are waiting for the supernova. Shortly before the event, they update their detectors. They also set up new experiments to confirm exotic theories. The detectors are located at different distances from the star, depending on what they are supposed to measure. There are close-in experiments at less than 100 astronomical units. At this distance, the instruments are expected to receive 300 million times as much radiation as the Earth receives from the Sun. These are special constructs with shielding of at least 1,000 kilometers. In practice, they are cylinders of 1,000 kilometer length, with alternating sections of field generators, mirrors, cooling elements, conventional radiation-repellent armor, and large engines against the radiation pressure. The scientific instruments are on the far side of the cylinder. Other sensor networks form spheres at a distance of light weeks or light months to measure asymmetric effects accurately. For many research institutes and their staff, this event is the highlight of the century. They invest a huge effort to take this unique chance. Even though there is a ridiculously large number of instruments from countless organizations, they do not get in each other's way, because space is so big. The only places where experiments pile up are the polar regions. At the poles, high-energy experiments are set up, because that's where a GRB, a gamma-ray burst, is supposed to provide physics experiments with the highest energy density in the universe. The event actually lasts for months. Although there is a single defined explosion time, the light of the explosion needs weeks and months to reach observers. The main optical wave front of the explosion is particularly impressive when the red hypergiant lights up, becoming 1,000,000 times brighter than before. That is a lot of light. The main wave of the radiation is only safe at a distance of several light-years for unprotected observers. At 15 light-years, the supernova shines as bright as the sun on the Earth. Humans and savants of other high-tech civilizations, having adaptive optics instead of natural eyes, can observe the supernova from as close as 2 light-years, provided they protect themselves from burns. However, the wavefront takes several years to get that far. Therefore, observers must either wait years, which somewhat spoils the event character, or they travel behind the wavefront with specially shielded ships to close into the remnants of the star. At a short distance and behind the wavefront, they can observe the afterglow, admire the new planetary nebula, and look at the newly formed black hole. A planetary nebula must be very impressive from the inside, if you catch the right moment, between different particle and radiation waves. The universe appears brightly lit, animated in real time and in infinite colors across the entire electromagnetic spectrum. Getting between radiation waves is called wavefront hopping. Modern spaceships can navigate along different wavefronts of the explosion. However, they must be careful to stay in front or behind a particular wavefront. Wavefront hopping is dangerous because ships are affected by radiation, whether the wavefront itself is moving or the space is pushed through the wavefront by the FTL drive. They can cross wavefronts only in protected regions, needing a barrier that can stop the radiation, and that is large enough so that ships can hide in its shadow. In this case, several large orbed objects and a brown dwarf in the vicinity serve as natural barriers for wavefront hoppers. Just before the wavefront is expected, a ship hides behind the barrier, waiting for the radiation inferno to pass. Then, with the wave ebbing down, the ship can leave the shadow and move closer to the star at FTL speed. They just have to make sure that they do not cross a wavefront accidentally, and that they get behind a barrier in time to let the next wave pass. Hoppers missing a barrier must stay in front of their current wave for years, until it has expanded so far that the radiation level is not lethal anymore. Many do this on purpose. They enter the supernova behind a barrier, and then drift back to safety for months or years in front of a wave, because exiting is even more difficult than entering. To get out of a wavefront, they have to overtake it at FTL speed while staying in the shadow of a barrier. If they deviate only 1/10,000th of a degree from the ideal path, they are lost. Worse, these paths are not linear, because a supernova always has asymmetric and chaotic components. Hoppers can reduce their risk by constantly resimulating the supernova and providing the simulation with up-to-date data. That is a huge effort. For this purpose, visitor ships, measuring instruments, and simulation nodes form gigantic networks, paid for by the wavefront hoppers. Particularly bold observers who want to experience the supernova without having to wait years, hide behind shields in the relative proximity of the star. Some fanatics stay only a few light days from the star. They are using shielding cylinders thousands of kilometers long like the close-in experiments. Of course, this is not cheap. What they do is not just experiencing the supernova, rather they are surviving it. Later they can boast for centuries about how they survived only light days from a real supernova. Nobody can beat that easily. These adventurers rely on computer models that are accurate but not perfect. If the supernova is only 10% stronger than predicted, then the safety margins are not sufficient, and all the advanced experiments, and all of those bold observers vaporize in the electromagnetic wavefront, in the neutrino flood, in the particle inferno, or in the expanding stellar shell. In this case they can use their backup, but unfortunately the memory of the event is lost. For some, this fate is intentional. They want to die in the supernova. Savants from high-tech civilizations can live very long lives. At the beginning they have an original genetically optimized biological body, then perfect biomechanical spare parts, and finally an android hosting their uploaded consciousness. For some people life becomes boring after such a long time. Can you imagine a better finale for a long life than to merge with the wavefront of a supernova in the certainty that the atoms of your body will form new stars, new planets, and new life? The supernova is not only a big physics event. The number of visitors is also overwhelming, even though only a small fraction of the galactic population attends. Only few civilizations master interstellar distances at this level. Furthermore, while long-living savants from high-tech civilizations have a different perception of lifetime, only a small part of each population decides to make the long, and usually not quite cheap, journey. Nevertheless, it is estimated that the total number of visitors is in the order of 200 billion beings. Many travel for several years. There are even reports of, and actually interviews with, visitors who traveled 20 Earth years from a region of the Milky Way 30 degrees spinwards. The supernova is truly an event of galactic proportions. Most visitors are from species that humanity has never heard of before. Even humans are strangers here. The human domain covers about 500 light-years, and humanity maintains relations with peoples up to 2,000 light-years away. Fast ships can make 2,000 light-years in 4 months. Beyond that, there are only sporadic contacts. The location of the supernova at a distance of 5,000 light-years is far outside the human sphere of interest. This also applies to most other visitors. They are far away from home. Much further than they usually travel. But the supernova is a very special event for all high-tech civilizations. The 200 billion visitors are spread over several years in time and space. They arrive with billions of spaceships, a tremendously large number. 30,000 ships arrive just from the human domain alone. But space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is, as the 20th century philosopher Douglas Adams said. Billions of spaceships are lost to cubic light years. The average distance between ships is larger than our solar system. Imagine there are 2 spaceships on the opposite side of Pluto's orbit and there is nothing in between. In other words, although there are so many visitors you almost never meet them. Nevertheless, there are places where you can meet other visitors, kind of. Visitor ships are 100 times more frequent in a disk around the equator of the star. The equatorial region seems to be special for most visitors, although the explosion is actually spherically symmetric. Only the poles, where the gamma-ray burst, the GRB, is expected, are really special. The equator is pretty safe from a GRB though. Maybe that's why people cluster there. The minimum distance for radiation-hardened ships is 40 to 50 light days. This equates to approximately 1 trillion kilometers. There is a ring around the equator, at the technically possible minimal distance, where shipping traffic is 2,000 times higher than in the rest of the sphere. With an average distance of only 1 billion kilometers, visitors almost step on each other's toes. The traffic becomes really dramatic in the shadow of large Oort objects, where the wavefront hoppers gather to get behind wavefronts. Although wavefront hoppers make only a few % of all visitors, the absolute numbers are so large that 4 million ships meet at each of the 20 Oort objects serving as radiation barriers. All these ships must fit into the shadow of a barrier. 4 million spaceships, from 10,000 different species crowd together in the barrier's shadow. Getting within 50 kilometers of each other they form a cloud of spaceships, 10,000 kilometers wide and 1 million kilometers long. A fantastic sight. However, it also makes for difficult maneuvering. The helms of these ships, being sophonts, infomorphs, or unconscious AI, do not know each other. They do not know their ways of thinking nor their navigation conventions. They do not even know the types of ships and their capabilities. They also do not have the time to get to know their neighbors. So there are misunderstandings and accidents happen. The number of accidents is quite low for such an extreme traffic situation. But the large absolute number still leads to 10,000 crashes with 3 million fatalities, by collisions or when ships are hit by others' exhaust. Far greater damage is caused by the unexpected fracture of an Oort object. A rather small stray planet with a diameter of 8,000 kilometers, at the 130 astronomical units mark, is struck by an eccentric micro-GRB, caused by one of the countless chaotic eddies in the core of the supernova. It was known that something like this could happen. It was known that gamma-ray bursts of lesser intensity occur off the poles in addition to the main GRB at the poles. But nobody had ever expected that one of them would hit an Oort object. The probability of this happening is ridiculously small. The stray planet consists mainly of water ice. It is more like a giant comet than a planet. When the micro-GRB hits, an ice wedge of 500 kilometers depth evaporates explosively within seconds. The Oort object disintegrates into many fragments drifting apart at 30 kilometers per second. After just 1 minute, the area that was right in shadow is suddenly illuminated by 11 gigawatts per square meter. That is 100 times more than the best ships can stand. Although everything is happening so fast, many are able to get to safety behind fragments of the planet. But 200,000 wavefront hopper ships with roughly 60 million beings are too slow. They evaporate and become part of the expanding radiation wave. 50,000 more ships are caught by exhaust rays of their neighbors who, hastily fleeing, navigate less carefully than usual. In total, there are 80 million victims. Most are from high-tech civilizations and almost all have backups, but their memory of the event is genuinely ruined. Only 60 light-years from the supernova there is a Kardashev 1.5 super-civilization with 10,000 billion individuals living in several neighboring solar systems. The first humans to make contact are high-energy physicists from a state research institute of the territorial sovereignty of the interplanetary asteroid belt near the gas giant Naradul in the Conquests system. The physicists have been setting up an experiment that will use the North Pole GRB, when some components fail that cannot be manufactured locally. While searching for replacements, they meet engineers from the supercivilization 60 light-years away, preparing their own experiment. They call them the Tau mass. The name Tau mass is derived from the term Tau mass because these alien scientists are conducting an experiment that is supposed to determine the mass of the Tau elementary particle to a very high precision. They are also using the North Pole GRB, because even though their civilization is much more advanced, they cannot produce such a high energy density in a laboratory either. Both teams describe their own experiment and that of the others in their languages. This is sufficient as a common basis to get automatic translators up and running quickly. The description of their experiments is the first complex information that the two teams exchange. This shapes the human scientists' perception of the strangers. And since the humans talk among themselves about the Tau mass guys, the term Tau mass sticks as a name for the entire species. In any case, the Tau mass can actually help. The defective components are replaced by the Tau mass fabs on the spot. As payment, the humans hand over their entire database of entertainment programs, because humanity's material assets or technical know-how is not of any value to the Tau mass, their tech level being quite a bit higher. Many other supernova visitors also visit the Tau mass. The Tau mass cluster is very impressive even for members of high-tech civilizations. Since most visitors spend months or years in the vicinity of the supernova, there is enough time to explore the region. Many hear about the Tau mass and visit their cluster. It is estimated that a total of 50 billion supernova visitors and 300 million ships take the Tau mass cluster as a tourist attraction. While visiting the Tau mass cluster, some humans run into man-Selu individuals which happen to be there in physical form or as infosophants. A statistical extrapolation amounts to 300 billion man-Selu individuals, in addition to the estimated 200 billion visitors of other species who arrive in spaceships like the humans. Rumors have it that the man-Selu come via a hyperchannel that connects the man-Selu complex with the Tau mass cluster at high FTL speed. But there is no independent confirmation. The Tau mass have the capacity for so many visitors. They know what is in store for them. And they are prepared. They not only take care of all those visitors, but they also care for their interstellar neighborhood. Only 6 light-years from the supernova, the Stone Age population of an entire planet is doomed. So aid organizations of the Tau mass move all 80 million beings and their biosphere into well-shielded artificial habitats. At a distance of 10 light-years, the existence of a planet-bound technical civilization with 20 billion people is threatened. At this distance there is no need to evacuate. Shielding helps against radiation while decontamination can neutralize the radioactive fallout. But the effort is huge, and the local civilization cannot cope at its tech level. Therefore, the Tau mass help to protect the planet. With their high-tech means they build a shield for the whole planet. They also provide the local civilization with facilities to decontaminate the biosphere, with fabs for the production of radiation shields and many other technologies that enable the local population to help themselves. Preparations are still underway when the supernova explodes. At that point there is still 10 years' time until the first wave arrives. Then a second sun illuminates the celestial bodies of the system. Only the home planet is completely protected. For the other planets, the supernova is brighter than their own sun. The outer planets receive 1,000 times more energy than before. This causes dramatic changes, but the local civilization can cope with that. After a few weeks, the supernova fades back. On the other planets of the system, effects of the energy flood remain for decades. Then waves of radioactive particle showers begin. First to arrive are almost light-speed fast protons and electrons. Only a few % penetrate the planetary shielding, reaching the atmosphere. Charged particles spiral down along magnetic field lines, and for some years there are fantastic auroras, even down to the equator. Next are heavier elements, starting with alpha particles, then fast carbon nuclei, with a high proportion of radioactive C14, which is bad. Finally, calcium ions and iron cores. Large locally built plants and tau-mass nanotechnology are working feverishly to filter radioactive isotopes from the biosphere. An artificial dust cloud cools the planet, compensating the energy input from supernova particles that heat up the atmosphere. A veil of smog covers the planet and makes wonderfully colored sunsets. 10 years later, highly enriched nuclei of heavy elements arrive, and nothing is beautiful anymore. Tau-mass forces block off all solar systems with indigenous populations within 300 light-years. Thus they prevent millions of spaceships in search of further sites from disturbing the local, often non-space-flying peoples. The Tau-mass also organize sightseeing tours through their own cluster, allowing visitors to admire the huge structures of Tau-mass Prime. Visitors learn about the cluster-wide multi-light-year real-time information network. With their own shuttles, they can even use the FTL converter tracks to travel almost instantaneously between Tau-mass population centers in different star systems. There are also guided tours to interesting sites of the interstellar region. For example, participants can observe the evacuation of a Stone Age population from Roanoke 4, including their biosphere, or the construction of a full-scale planetary shield for Iris B. In total, the Tau-mass guide 200 million visitor ships in a controlled way through the interstellar neighborhood. Thanks to all these measures, only few regional civilizations are disturbed in their development. Even the resettled natives of Roanoke 4 only vaguely remember later the time of great changes. Their descendants only know the world as it is, and when their elders tell at the campfire that there used to be no sky band behind the horizon, the youth just wonder a little bit, because everyone knows that the sky band holds the world together. The ejected shell of the former hypergiant expands at a rate of a few thousand kilometers per second. It will soon form a planetary nebula. 30,000 years later, the shock wave will compress the gas cloud that was always visible from the Sol system. This will trigger the formation of new stars, with their own new planetary systems, and maybe new life, as it has always been. What humans do not know, and probably no one below the level of supercivilizations like Tau-mass and Manselu, the atoms of 3,000 billion Manselu are being blown away by the new planetary nebula, a perfect opportunity for them to become one with the universe, and so easily accessible via intercluster expressway. Most visitors leave the region of the supernova after months or years. They return home, taking with them the memory of a truly galactic event, the supernova, the Tau-mass cluster, 10,000 species, and millions of ships. It gets quiet around the former red hypergiant. Only the black hole remains, and a quadrillion abandoned instruments. This was Galactic Developments, year 3308. I am a physicist and I have always been interested in history. That's a good combination for the history of the future. I want to stay as close as possible to reality. Above all, this applies to technology, which should be scientifically sound, or at least reasonably explainable. But it also applies to social and economic developments. If you think that I have presented something unrealistically, write me in the comments. Or, if I've raised more questions than I've answered, please also ask me in the comments. If you like the video, please hit the like button. If you subscribe and click the bell icon, you'll be notified of new episodes. Of course, sharing on social media would be nice. More events from the future can be found at galactic-developments.com. If you have a futuristic topic you'd like me to discuss, drop me a line. If you want to use an idea or add something yourself, feel free to do so. There are already hundreds of events, but I would love to read other stories from this future. Write me if I can help. The future starts now.